Hello, everyone. Welcome to panel two, session one of summer study, where we'll be talking today about the giving you some examples and stories around electrification and alternate fuels in industry. Thank you for joining once again. My name is Kate Peretti. I am a technology manager in the Advanced Manufacturing Office at the Department of Energy, and I will be moderating this session. I have a few housekeeping items to start out with. First off, I wanted to give a little bit of a plug for the additional sessions that we've put together for panel two. Today, again, we'll be talking about some examples and stories around electrification and alternate fuel deployment in industry. Tomorrow, there are actually two sessions, one that's more analysis focused, and then the second is on use of alternate fuels. And then on Thursday, we will have our final session on technology development in this area. So lots of great speakers, so please tune in to all of those sessions. It'll be great. So first off, I want to say thank you to all of the sponsors for making this event possible, especially DTE, the host sponsor. I don't see what you see, but there is a sponsor link on the left-hand column of your page that you can click to visit their site and learn more about their work. We have an exciting lineup of speakers today. The way that the session will be run, all of the presentations will be given sequentially, and then we'll have 15 minutes at the end of the session where all of the speakers can answer questions from the chat. ACEEE will collect the remaining unanswered questions and send them to speakers to respond to after the conference if we don't get to it in that 15-minute time period. With this in mind, you can see the chat box on the right-hand side of your screen, and please use this only to ask questions. I see there's already some chatter amongst participants. If you want to connect with other attendees, please take advantage of the attendee link, also found on the left-hand column of your page. Any attendee who's created a profile can be found there, and you can take those chats in that area. In the resources column, you'll find attendee resources as well. They contain the conference proceedings, the attendee list, and an evaluation survey to complete at the end of the conference. Anyone who fills it out and includes their name and testimonial will get a discount to attend the 2023 summer study. In the program participants link, you will find information about all of the presenters, including bios and copies of their presentations. Last, please join us at the end of the day this afternoon for post-panel debriefs to learn about other discussions that you may have missed. And remember that all sessions will be recorded and available on demand after the conference. All right, with that, now we're ready to get started with the speakers. So I'm going to kick things off with Srinidhi Krishnamurthy. He is a senior engineer at Electric Power Research Institute, EPRI. He works with electric utilities to advance the deployment of electric power technologies in commercial, industrial, residential, and transportation sectors. He also works with industry partners around the US and internationally on energy efficient end use technologies. And Srinidhi has a PhD in mechanical engineering from UC Davis, and he has 10 years of industrial experience prior to joining EPRI. So with that, I will let him take it away.
Yeah.
And
thank you, Kate, and hello, everyone. As Kate mentioned, I'm working at the Electric Power Research Institute in the Electrification program. And today I'm here with you all to talk about the non-energy benefits for industrial electric technologies. And this work was done by me and my colleagues, Ikram Lagwidi and Rick Ranhotra. And Rick is with us as well on the call today. So I would first of all like to tell you a little bit about my organization, EPRI, and our research focus. And following this, I will introduce the topic of our presentation the motivation for this study, and I will cover what we mean by non-energy benefits with some examples and how they can be quantified in the life cycle cost calculations. And also, I would like to show some of the impacts of including the non-energy benefits and some important considerations while doing so. So who is EPRI? We are an independent, not-for-profit organization that conducts research and development for the generation, delivery, and the use of electricity, and as well as for alternative fuels. And we work with more than 450 participants in more than 30 countries. Our members are primarily electric utilities, and together we shape the future of energy. We have multiple research areas like nuclear power, renewable generation, transmission and distribution, integrated grid, and also the program that I and my colleagues we come under is the Electrification program, which is part of the Electrification, Environment, and Sustainability sector. And in the Electrification program, our core mission is to benefit utility customers, which in turn benefits utilities. And we build effective models. We develop comprehensive knowledge base related to electrification technologies and do rigorous market studies. And we do all this collaboratively with an engaged utility group. So now let's come to the topic of the study. As we all know, electrification is an important pathway to decarbonize the industrial sector. And it's a sector that's one of the hardest to decarbonize. And electrification of the industry has a good technical potential because a lot of technologies in the industrial sector are available to do so. But the economic considerations are more important in this sector because many of the technologies have a long-term investment, and hence it's very important to make sure that the customers are finding the technologies cost effective so that they actually can find value in the technology. So it's important to know that in such a case, like any additional value that can be provided for to show the benefits in an electric technology will be useful for the customer. And that's what our study was motivated by. We are trying to show some of the non-energy benefits that we can be included in the cost calculation so that those can provide additional value. So non-energy benefits as a cost reducer. Firstly, what are the non-energy benefits? These are like when customers buy electric technologies, one primary selling factor is a lower energy costs. But there are benefits beyond just the energy savings that or some of the avoided costs of the energy from the utility that can be used as non-energy benefits. And you can see on the picture in the right side some of the examples of non-energy benefits like productivity, product quality, health and safety benefits, environmental benefits. And the significance of these benefits is that they can make the electric technologies become cost effective and allow the customers to more appreciate the technologies readily. And from a utility perspective, electrification programs can be successfully promoted to the customers, and also the inclusion of non-energy benefits helps achieving energy policy goals. So the challenge with some of the non-energy benefits is how to account for them numerically. And some of the non-energy benefits can be quantified or monetized. For some others, it's not so easy to do so. And this is a table here, a simple example with different non-energy benefits and the quantifiability. One simple example is that if the product quality, the improved quality as a factor under product quality is characterized by improved product taste and appearance. like improved product taste is somewhat harder to quantify because it's very abstract. But the key message here is that regardless of how easy or difficult they are to quantify, it's important that customers are made aware of different non-energy benefits, because they can affect the investment decision on whether they can be whether they would consider the technology or not. And so in this study, we take two examples to illustrate the quantification of non-energy benefits and show them in the overall cost analysis. The first one that I would like to show is is an example from the food processing industry. It's the use of infrared dry peeling for like peeling of fruits and vegetables. And in infrared, previous research has shown that infrared peeling has several advantages over traditional live peeling method, like lower peeling loss, firmer products, and reduced water use, etc. And on the and similarly on the other side, like on a primary metals industry, there is we take the example of induction melting. And induction melting is used to melt iron and other metals instead of the cupola furnace as an electric technology. And similarly, there are advantages for using induction melting, like faster melting, higher melting effectiveness, and improved precision and product control. So now, if we use these examples to actually quantify the non-energy benefits, like for the case of tomato peeling, or the peeling of fruits like pears, one example that we have shown here is that the raw, like in the previous slide, we saw that there is less raw material being used for peeling because there's less loss of raw material. So the raw material cost savings are quantified as, like, if there is a 10% reduction in the use of raw materials due to the use of infrared technology, and let's say that the price of raw tomatoes is $100 per ton, just as an example, then that saves $10 a ton for additional cost, apart from the energy savings that come from infrared equipment. And similarly, for different other fruits like pears, 10%, and then the raw material price. So there can be different amounts of savings depending on the application and the technology. And similar example can be given for the induction melting, like the productivity improvement that I pointed out for as a non-energy benefit. So let's say that there's a total of 8,000 plant hours that's being used in a year, and 10% time is saved by the use of induction melting. So that means that for a labor rate of $100 an hour and a production capacity of 4,000 tons in a year, about $20 per ton of iron is saved due to the use of induction melting. So now what we'll do is to check how these calculations can be used in a life cycle cost analysis, and that we'll see the impact of the use of non-energy benefits on the cost. So we are seeing here that an example of the food processing industry, again, coming back to the infrared heating, compared to a convection oven. The table here shows the life cycle cost calculations for without including any non-energy benefits. So there are some the equipment cost, the energy cost, the maintenance cost, and we see that the capital cost is slightly higher for the electric equipment, but the life cycle cost is actually somewhat favorable even without including the non-energy benefits. And so just based on life cycle cost, if a customer were to choose choose between one of these two equipment, we can calculate an adoption potential And in this study, we calculated the rate of adoption using a logistic regression model of about 51% for the infrared heating equipment, simply because the life cycle cost is somewhat lower. But what happens? So what happens when there is a non-energy benefit included? So we look at three scenarios. One without the non-energy benefit, which we just looked at, and then there are two other scenarios where we consider that. Let's say that the non-energy benefits for infrared heating accounts for 40% of the life cycle cost savings. So the 40% means the cost, the total life cycle cost is reduced by 40%. And so the infrared heating, which originally had a life cycle cost of $995,000, now the adjusted life cycle cost becomes $595,000. And with this very different price compared to the convection oven, the economic potential actually increases. The adoption potential due to the economics increases quite a bit. And a third scenario is also considered where the non-energy benefits can actually be higher than what the actual cost of the life cycle cost is. So this is somewhat, in one sense, it might be that this might be, really depends on the application, on how much is the cost savings due to a certain technology or a certain application. But it is very much possible that in industrial settings that the benefits provided by technology is much more than actually what the cost of the life cycle cost of the equipment is. And in such a situation, there is virtually no cost being borne by the customer. And so the electric technology becomes a clear winner in this case. Similar example is shown for the induction melting furnace compared to the gas furnace. And here again, with the cost data that are shown here, we see that just based on, without including any non-energy benefits, the induction melting equipment is somewhat has an adoption potential of about 30% due to its higher life cycle cost. And so if it's only based on economics, the customer is likely to choose the alternative option usually. But when the non-energy benefits with the similar scenarios are included, we see that there is a clear difference in the economic potential. And so based on the adjusted life cycle cost of 40% and 120% respectively, the potential or the chances that a customer will choose the induction equipment is much more higher than the alternative equipment. And here's a graphical view of the same situations, the same type of the different, summarizing the different types of adoption for melting and drying applications. So I would like to also point out that there are some important considerations while monetizing the non-energy benefits. Like we showed a couple of examples, but in reality, the different types of applications and even for the same equipment may vary a lot. So the characteristics of non-energy benefits may depend on the type of the technology. For example, infrared equipment can be used for peeling tomato or peeling pears, or it can be like infrared heating can be used for like heating French fries, for example, in the food processing industry. And the way the non-energy benefits are calculated in frying the French fries is the lower oil loss, as opposed to like the raw material being saved there is oil, and unlike the tomato peeling where the raw material being saved is tomato. And also the non-energy benefits can vary in the level of quantifiability. So it's very thorough study is required to actually do some measurements the values that I showed were more example values. So careful research is necessary. So with that, I would like to focus on some of the key takeaways for our study. That the non-energy benefits is an important factor that influences the economics of an electric technology. And we looked at some of the examples like productivity, product quality, reduced processing time, health and safety, and environmental benefits. And it's important to also note that the non-energy benefits have greater value when the energy savings do not have as much attention, because in that case, the impact on the life cycle cost is much more lower. So when the non-energy benefits have to be particularly considered when the energy savings are not as attractive to the customer. And with that, I would like to end my presentation and turn it over back to Kate. Thank you all for listening.
All right, thank you, Dr. Krishnamurti. Next up, we have Jonathan Tebow. He is an energy consultant at VEIC, which is a sustainable energy company, where he focuses on providing technical services and commercial and industrial customers interested in managing their energy use. He works closely with pulp and paper, lumber, furniture, plastic, aerospace, grain, granite, and other manufacturers to improve energy efficiency, reduce waste, and lower operating costs. Prior to VEIC, Jonathan worked at MAN Diesel and Turbo, where he developed technical knowledge of diesel engines and power generating equipment, which is proven useful when working with customers and distribution utilities to evaluate the switch from diesel powered to grid electrified operations. I do want to, yes, please, I agree with thanking the speakers, but I would also like to encourage you to use the chat for questions. Don't save up your questions, please, until the last 15 minutes when we'll be taking questions. As the speakers are presenting, feel free to enter questions into the chat as they come up. So yeah, with that, I encourage Jonathan to please take it over.
All right, thank you, Kate. My name is Jonathan Tebow. I'm an energy consultant at VEIC, working predominantly with commercial and industrial customers. Today, I'll be presenting on the topic from diesel to electric, how energy efficiency and electric utilities can partner to electrify rural manufacturing operations. So just a quick rundown here of what I'll be talking about briefly. I'll introduce who VEIC is, some of the rural decarbonization challenges here in Vermont that may or may not be unique to the nation, tips for effective distribution utility and energy efficiency utility partnering, and this is just based upon our own experience to date, how you can improve customer responsiveness when trying to reach customers and convince them to electrify, and some case studies and results from the collaborative work that we have completed thus far with our distribution utility partner. So very briefly about VEIC. VEIC is a nonprofit mission-driven company located in Vermont. We work through our consulting arm on various projects such as electrifying transportation, energy efficiency as well. So energy efficiency is really a core focus of what our company here does. As such, we operate the Efficiency Vermont brand, and that is a statewide or state-appointed energy efficiency utility program here in the state. We also operate an energy efficiency utility in the District of Columbia, a elective one out in the state of Ohio, and we also manage and operate these other brands shown below. So moving on to the main topic, rural decarbonization challenges, and this is again relative to the state of Vermont. So I'll be speaking on behalf of my role here at with VEIC. It's on behalf of Efficiency Vermont, who is again a customer of VEIC, as well as Vermont Electric Co-op, who has given their full support and has been a partner for the work that I'll be presenting on here. So the situation in Vermont when it comes to electrification. So I realize this is a national audience, so I'm not sure what people have in mind when it comes to Vermont, but I'll tell you that Hollywood is probably not that far off. We are generally a pretty rural landscape. So things that might come to mind, such as farms and B&Bs and pasture lands and forests and mountains, rivers, lakes, you name it. It's a very natural landscape. And you can see there's a map in the middle that is a relief map, kind of shows you a bit of the topology of the land as well. It can be challenging for electrifying. There's a lot of corridors that don't exist for power lines. And so electrification in the state is more or less kind of compressed around areas where there's concentrated manufacturers, for instance, or residential hubs. The state itself, really briefly, where there's about 260,000 utility customers. That's not very much. I think we're about 4% of the total ISO New England load, so we are very small as a regional player as well. Despite only having about 250,000 customers, electric utility customers, there are 17 regulated distribution utilities within the state. We are not a deregulated electric market over here. So that means you have potentially some very small electric entities, distribution utilities with small budgets and a small customer base as well that are having to do increasingly complex things and are being stretched on their resources. A few things to point out here on this slide as well. The average retail price in the state for electricity is about 15 and a half cents roughly. This is important to note because electricity, as most people may be familiar with, is pretty expensive in the northeastern part of the US. And yet, despite this, many of the customers that we're dealing with these line extensions have found an economic advantage to converting. Hearing something, please. Can you still see my slides? Okay. Moving forward, Vermont Electric Co-op, who is, again, the partner in this work, they have about 32,000 members and serve about 2,800 square miles. This makes for a very low density for a customer network, as well as a very low density or intensity for electric usage. That means they have a lot of network to maintain with little electric sales and electric sales revenue to do so. So it creates some constraints in terms of investing in electrifying new customers. This is a quick overview of their map, of their three-phase distribution map. The purple lines shown here are basically their three-phase corridors, and you'll see there's a bunch of little islanded areas out through the mountains here, some dead-end networks that don't connect through, and this is just because of historically the lack of need for three-phase power in a lot of these regions. However, it creates a complication in that any new customer looking to come online or a customer that would be interested in making the switch or the conversion, if the three-phase power is not running already through their dooryard or at the end of the street, you can have some rather lengthy line extensions, which make the cost to connect pretty cost prohibitive or pretty high. So the challenges with electrification from the customer perspective is that it can be expensive. Historically, the customer has incurred almost the full cost of the cost to connect to bring electricity to the property. So this can be challenging for the customer if they, again, have to bring that line in miles. Seasonal operation and demand charges have also posed a historic barrier. So if you have a manufacturing operation, for instance, such as a sugarer, maple syrup sugaring, they only operate typically 1 to 2 months a year. And so if there's a demand ratchet where they have to pay a demand fee for the next 10 months of the year, it makes the cost of electricity or the cost of energy, in this case, very expensive. And then there's also cost apprehension, because most customers who are buying fuel and fueling generators to power their operations are very aware of the sensitivity and volatility of fuel prices. So below is a 15-year trend of the cost of diesel, the price of diesel in Vermont. And you can see it fluctuates wildly from $2 as a low roughly to over $4. And it stayed there for almost a period of about 4 years even. So if you're a customer running a diesel generator and diesel's $4 a gallon, you probably are going to be calling your utility to see how much it costs to connect. But if it's $1.50 or $2 a gallon, like we saw, a few summers ago, the urgency to electrify via the grid diminishes because the cost effectiveness of it decreases accordingly. Then there's utility challenges to connect these customers. So you'll see at the top here mentioned Tier 3. Vermont has very aggressive goals for decarbonizing the state and introducing renewable energies. So much so that they're pledging 90% renewable energy by the year 2050. Part of the structure for their renewable energy or their transformation of the electric system here is what they call Tier 3, and that is to bring in new loads or convert loads that were fossil fuel or carbon based and bring them onto the grid. And there is now, as of 2016, every utility is required to participate in a scheme to move more of these fossil fuel based customers onto the electric grid. And each utility has their own unique goals, and failure to achieve these goals and their annual goals, and it's basically a BTU to megawatt hour switch. Failure to achieve these goals will result in a penalty actually assessed to each utility. And so now there's a financial priority as well, a prerogative for the utilities to reach even further than they were before and harder than they were before to try and electrify new customers. Again, this can be challenging though, because there's competing investment priorities such as antiquated infrastructure, which is compounded by limited revenue just because of a low electric sales market. There's not a big industrial customer here that can really take on a lot of the cost sharing for this. It's a lot of houses, a lot of small businesses, and so the utilities are trying to exercise financial restraint as well and not have to put the onus back on their customers to finance these improvements. So Vermont Electric Co-op, how they've chosen to meet the challenge. In 2016, they introduced their Clean Air program, which with that program, it introduced new time of use rates that are demand free. And these are exclusive to new customers coming on grid. And so it alleviates a lot of the concern that those maple sugarers, for instance, had, that seasonal sawmill operators have. Another seasonal operator that we see is sand and gravel or asphalt operations. These companies, just based on our seasonality and our harsh winters, might operate 9 months a year, but have a large demand. And so having a demand-free rate changes the financial outlook for grid electrification significantly for this customer base. For customers that are still, philosophically still too far to reach, beyond the end of the line, Vermont Electric Co-op actually led the initiative to reach out to Efficiency Vermont to electrify or to partner on some of these more challenging projects. And we'll talk briefly here at the end of this presentation about a few of those customers. Since deploying or embarking on their Clean Air program, Vermont Electric Co-op has completed 19 of these projects to date, have 4 additional agreements in place, and are in pursuit of equally more at the present. So tips for effective distribution utility and energy efficiency utility partnering. And again, this is really just lessons from Vermont Electric Co-op and Efficiency Vermont's joint decarbonization efforts with these customers. So first and foremost is the energy landscape, as you're all aware, has changed a lot in the last 10 years. What used to be a defining point between an efficiency utility and a distribution utility was the customer's electric meter. Typically, everything above the electric meter was the jurisdiction of the distribution utility, and the efficiency utility worked with the customer behind the meter inside their walls. And so this limiting interface kind of kept everybody in their lanes historically. But what we're seeing is it's not beneficial when we're talking about partnering and working to electrify new customers. Primarily because the electric utility might have, for instance, some restrictions on their ability to serve on parts of their network if they're already at a critical line load, or other concerns that the energy efficiency utility might be able to lend support on or provide insight or clarity. As a general matter, I work a lot with sawmills. So for instance, I knew there was going to be an issue coming with power factor, and I was able to call that out to the utility ahead of time. And so that makes a difference too when it comes to balancing. If you're just measuring amperages, but you're having to size transformers and things like that for KVA, having that insight ahead of time that this type of load might have this type of impact on the utility is very powerful for them. Another bit of understanding is that when things might be a little bit more closed-handed, or at times as you're starting to work with a new partner, we've typically sat across from the table from each other, not on the same side of the table. And so building some honesty and some transparent communication and giving trust to your partner in the beginning was very important. And knowing that they're coming into this with the right intentions and the right expectations. And it's an exercise to build trust, of course. But you have to give your partner the benefit of the doubt and assume that they're going to do the same with you. And it worked out fantastically in this case. And when you do have those sticky points, remember that the common core here that is bringing both partners to the table is that we both genuinely care about fostering economic development, and we care about the livelihoods of the customers we're dealing with. Nobody's going to want to encourage a customer to connect to the grid if doing so is going to put them at a financial disadvantage and harm their business. Decarbonizing a business is not going to do the customer any good if they're out of business in 2 years. And so keeping the customer at the forefront of all the work that the distribution utility and the electric efficiency utility were doing really helped to kind of keep perspective as we work through some of the finer details of a new relationship, and also how to engage a new customer comprehensively. And be patient, be flexible. And this is new territory in a lot of cases, and so the answers are not necessarily already going to be there. They're going to have to be figured out, and that's going to take some time and some flexibility. So keep that in mind. Don't get frustrated. Keep in constant communication, and good things generally happen. Tips to build trust between partners. So in this case, Vermont Electric Co-op approached Efficiency Vermont first, and one of the things they're concerned with was they have a lot of time invested, with these customers already. They might have already been working with them for 2 years and put multiple proposals on the table to electrify them. They don't want to be this far along in the game and have a partner or a potential partner come in, and swoop them away, because we could work with them from the perspective of thermal efficiency as well, on a BTU basis. So an upfront expectation that the lead who brought the customer to the partner is going to maintain kind of control of that project, unless it's determined that by both partners that it'd be advantageous for the other partner to take the lead. Show up together. It's as simple as that. Any consequential communication should be coordinated in advance so that there is a consistent message delivered by both the efficiency utility and the distribution utility, so that the customer is not confused and isn't feeling like they're being gamed or forcing them or joining in the game, figuring out which partner to ask which questions. That's corrosive to a relationship as well. So maintaining transparency, it's expected that both parties will be able to speak freely and willingly with the customer directly about any matters that they want. However, it's encouraged that before reaching out to the customer, that you check with the partner and make sure that they didn't already request that information first. So that way the customer is not having to answer the same questions twice. And likewise, when you receive new information from the customer, that you share it with the partner, and so that there's no overlapping communications that add just administrative work on the back end for a customer and lead to a more exhaustive effort. Promote efficiency improvements. So one of the things that we found through our work is that, again, going back to maybe power factor as an example, if you correct the power factor, would it lead to a smaller transformer? Possibly. In doing so, also would then bring down the cost of a line extension, since the cost of a transformer is now reduced. So looking at things, beyond just bringing power to the site, but how the power, qualities of the power, as well as how the power is used, and opportunities for improvements such as VFDs and other energy saving matters should be taken or conducted at the start of the project. That way equipment can be right sized and effective and potentially bring the cost of a project down. Advocate for the customer. Again, this goes back to that point on both partners taking pride in being an advocate for the customer and their overall well-being and health. And so if there's at any point, any concern, both partners reserve the right to throw up a flag and say, hey, I'm concerned that this might not be a good direction for you to go. There should be no concern that, either partner is going to torpedo a project, so to say. It's really meant to be to give each partner the ability to communicate directly and openly with the customer. And then expect to share savings and savings credits. So if there's an incentive that's being applied, a common incentive, and there's a savings pool. So in this case, it might be like an MMBTU credit or a megawatt hour goal towards tier 3. If an incentive is being applied, it should be expected that some representative credit is also going to be given to each customer. And that's really just to emphasize that both organizations work with a finite budget and have to meet goals. And so expecting one customer to contribute financial resources and have no gain towards their goals might put them in a difficult position. So just those could be negotiated at the time of each project, but it should be pretty, transparent walking into this that there might be an expectation to share. So furthering the chance for customer success. One way is to potentially get creative with incentives. And so what we've done in a few situations is you can incentivize a line extension directly, and then you're basically just contributing an additional incentive to what, and when I say we, I mean Efficiency Vermont, we contributed an incentive on top of what the distribution utility was offering the customer an incentive for a line extension, so that it was a total lump sum incentive to bring power to the site. And in that case, we would split the offset fuel savings as well. We've also worked effectively to, in one case, we were able to support a variable frequency drive for a centrifugal pumping application that was run off a diesel engine before. So the project there was to convert a shaft-driven pump to an electric operation, and the utility took the project up to the disconnect, and then Efficiency Vermont supported it from the disconnect to the pump and was able to do so via an incentive for the variable frequency drive, which allowed us to claim electric savings versus a baseline and allowed the utility to claim the full fuel offset. So to the customer, it looked like one total incentive, but on the backside, the distribution utility was able to take away the fossil fuel savings, and the efficiency utility was able to look at it as in the classic lens of energy efficiency savings and electric savings to pull towards their goals. One other thing is just sometimes these customers, they have they're small mom and pop operated businesses, and so they have small budgets. If they're having to pay for a line extension, that might divert some of their financial resources away from maintenance activities or other slated capital expenditures that would lower their electric usage. So we've also, in one instance, supported a cash incentive to the customer to help at the time that they connect, to do some of these maintenance improvements so that they don't put themselves in a limited situation where they have to defer maintenance and consequently spend more energy. So get creative with how you apply incentives to these projects. Third party, not third wheel. What this really means is that, so because of tier 3, the distribution utility is now required to save or to connect some of these customers. So that puts a little bit of a natural tension between the distribution utility and the customer, who now feels like the utility is trying to sell something. So if the efficiency utility can come in and assert themselves as a neutral party that is basically vested in the customer's best interest and work alongside the customer to vet the opportunity, they'll have more confidence when it comes to the time to make a decision that all avenues have been explored, that the finances have been worked out for this, and that they're not just being sold a line and that rates are going to change next year. And it just brings more confidence to the customer. So improving customer responsiveness, how do you get them to convert and take on new projects? Again, here, the key is transparency, show everything, hide nothing. So that really means show all of their current operating costs. Don't just focus on what they spent in fuel last year, open it wide up to their maintenance costs. We've seen sometimes that customers, if you look at their annualized maintenance for generator rebuilds, oil changes, we had one customer that's having to do rewinds every 3 years. It can be excessive and it can change the finances of a project. Future operating costs, so that means we would take the customer's load profile and project forward what their electric bill might look like. And so they could see what their current cost is versus their future cost. And then that would be, that margin would basically be applied towards the cost to connect the customer. And really here, this should be as comprehensive as possible because it gives confidence to the customer. So in this instance, the utility will quote the line extension, but a lot of times there is also work that needs to happen on site as well to bring electricity to the final piece of equipment. So conduit, electrical equipment that's in the building that has yet to be completed, power factor correction units, all these costs should be included in the total cost to electrify the operation so that the customer knows this is my full cost, this is what I'm going to save, and this is my payback. This is what I need to borrow from the bank as well, take out in a loan. That's been a huge benefit that customers have shared with us, is giving them this kind of comprehensive analysis gives them material to bring to a loan officer and actually get financing for these projects and gives them some certainty. So giving them the full picture, don't hide any details. It's shown dividends, so to say, as we've moved to convert some of these projects. And then highlighting the non-energy benefits is also very important for some of these customers. So we just touched on reduced maintenance costs, but also Vermont's cold. We have customers who complain that their generators freeze up and they lose a day worth of production, or the fuel itself is water and it freezes. And it can be a nightmare. And that's another cost that if they lose so much time due to generator maintenance or fuel outages, that can be included in the economic evaluation as well. Noise abatement. In some cases, we had a customer who had a generator inside the facility and had it in a combined heat and power application. Great for heat recovery to have it in the building, terrible for the workers and noise and vibration. So they were really excited to get rid of the generator because it was not good for a human health type situation with the working environment. Operational expansion, the second customer we worked with was able to increase the capacity of their operation by over 25% after they connected to the grid, whereas they would have needed to purchase an additional generator just to run that one operation had they not gone on grid. So expansion of operations is another non-energy benefit. No more knocks on your door from state inspectors for air permitting. In environmental purposes. One customer told us straight up that they were willing to convert just for that reason alone, even if it meant, taking a slight loss. They did not want the level of harassment as they described it anymore. So again, another non-energy benefit. And then improved power quality. We had a customer report they couldn't use VFDs for their process control because they didn't have stable enough voltage, and they had tried it and they were losing equipment. The drives were failing. So having a regulated supply of electricity is another non-energy benefit. And then just real brief, a couple of customer highlights here. The first project we completed saved about 38,000 gallons of diesel, and this was an off-grid sawmill that operated 9 months a year. And then another customer just down the road, actually, they've completed 2 projects already. The first was to electrify a sand and gravel operation, and the site located asphalt plant as well, and that saved about 46,000 gallons of diesel. They've since gone on to electrify a dewatering pump and have grown their operation again. So now they're saving upwards of about 55,000 gallons of diesel a year that were used for nothing other than electrifying their operations. And then this is just a summary kind of some of those takeaways on just those three highlighted projects alone. So about 2.4 miles worth of three-phase line extension, little less than $500,000 in project cost to make that connection. The total incentive provided by the distribution utility and the energy efficiency utility through all incentive avenues was about $245,000. To date, that's saving about just over a gigawatt hour a year of electricity. And that's about 90,000, just shy of 90,000 gallons of diesel every year that have now been displaced for electrification, equating to about 393 metric tons of CO2 savings a year. And this number will actually increase as the grid becomes cleaner, which again, Vermont has those regulations in place for 90% renewable by 2050. And as well as this is a 30-year measure life. So if you were to consider at 400 metric tons a year, that's about 12,000 metric tons of CO2 that these three projects will save in their lifetime. And this is really only the beginning. Again, we have many more projects already that have come to an agreement and many more that are in the works. And it's really been fruitful for the both the relationship between the energy efficiency utility and distribution on other fronts. And it's been a successful model to the point where Efficiency Vermont now applies the same kind of partnership model to other distribution utilities in the state and have seen similar results in effectiveness. So hopefully others on this presentation, viewing this presentation, might see some value in this model as well and be able to export it to their own vicinities. And that's all. I think we'll take questions at the end.
All right. Yeah, really interesting, because I'm sure this isn't the only example of where, benefits and costs cut across boundaries of things. So it's a really great example of how to negotiate some of those trade-offs. And thank you to the attendees for adding questions to the chat. I think we have a really great group of questions starting out. Our final speaker is Christina Chang. She is a fellow at ARPA-E, where she conducts workspace analysis within industrial decarbonization, including zero-emission production of iron and steel. Dr. Chang completed her PhD in physical chemistry at Harvard. As a Marshall Scholar, she completed her master's degrees in chemistry at the University of Cambridge and mechanical engineering, which had a focus in sustainable energy futures at Imperial College in London. She graduated summa cum laude from Princeton University with a bachelor's degree in chemistry as well. So please join me in welcoming Christina.
Hey, thanks so much, guys. Is the audio working okay? I will assume so. Hearing no complaints. First off, I may have shared some of the precursor slides to this final deck. So if the PDF that you download says embargoed on it, then just please email me for this finalized deck. So sorry about that, and email me for the PDF if you need it. Excited to share with you what we've been thinking about at ARPA-E in terms of green steel. To briefly introduce our organization, ARPA-E is the Advanced Research Projects Agency Energy. We're a funding agency within the US DOE, and we've been around for about 11 years. And in that time, we focused on our main missions to reduce energy imports, improve efficiency, and reduce emissions in the United States. And recently, within the past year, we got 2 new mission areas added around nuclear fuel and resilience. And in this 11-year or so time period, we have provided about $2.8 billion of funding to US researchers. And that money has turned into more than $5.4 billion of follow-on funding from the private sector. I also highlight here that over 700 patents issued here in the United States related to our projects show that we really do care about commercialization. And my final intro slide for you is just to say that at ARPA-E, we're trying to fund sort of moonshot technologies, stuff that if it works, it will matter, and it's highly risky. So as you can see in these several blue curves that didn't quite make it to commercialization, we're trying lots of shots, but hopefully one of them or so will make it to the goal, namely displacing existing technologies with breakthrough solutions. So let's get into the iron and steel sector. Looking at global steel demand, we see that iron and steel is, of course, really the elephant in the room when it comes to industrial emissions, perhaps tied for #1 with cement. And as we look at that iron and steel sector, of course, there's a value chain with several steps. And I tend to lump ore processing in with iron making because those technologies are coupled. How you process the ore dovetails into what iron making technology you use. And so when you look at that major sector of this value chain, what you see is that 5.5% of global emissions are due to iron making. And so this is the majority of emissions from the steel sector is due to iron making. So let's dive into why those emissions are happening. And of course, the answer is CO2 is emitted in the chemical process of making iron. So you take ores, iron oxide, and you react it with coal. And that turns into the reduced metal, the iron, and then CO2 as a byproduct. And unfortunately, coal has two uses in this reaction, so we use a lot of it. The first use, like I said, is it's a reductant, and it drives off that oxygen off the ores, but this releases CO2. And second, and actually the larger volume use of coal is just for heating. So oxygen is blown through these blast furnaces, and the coal reacts with oxygen, forming CO2 as well. So you can see a lot of coal is used for these two uses of coal, but of course you might consider, if you're reinventing a new process for iron making, decoupling this reductant from this heat source. They don't necessarily have to be the same species, and they certainly don't necessarily have to be coal or even carbon. Finally, I do want to mention two quick things. First, I've shown that carbon monoxide, CO, is the active reductant. That gas, CO, is actually the species that does this reduction chemistry, and that's important when we think about new technologies. And finally, you might ask, well, how much energy does this use, this process? And depending on your blast furnace and how modern it is, you might be using between 13 and 20 gigajoules of energy per ton iron, and that is a lot. And we're all efficiency wonks in the room, and so the question is, well, how low could you go in terms of energy use with this process? And so to satisfy our curiosity, let's look at the thermodynamic minimum of energy you could use to reduce iron ores down into iron. And that is shown here that at room temperature, you could use as little as 6.6 gigajoules per ton. And if you require molten metal, as most applications do, that bumps up to 8.6 gigajoules per ton as your thermo-min for molten iron. So I want you to keep this 8.6 in mind because that's our floor, but I'm going to take you on a one-slide detour before we look at the energy balance for several options, because you make iron, but then you have to turn it into steel. And so really technologies need to dovetail with steel making, and we need to look at the steel making technologies first. So in the United States, shown in blue, we produce about 89 megatons of steel a year here, and we import another 1/3 of our steel. So focusing just on those blue domestic production side, we have two ways to make steel. Shown here is that long value chain where you take coal and ores and you put them in a blast furnace. Then that molten iron goes into a basic oxygen furnace, a BOF. So this BOF is the main way that we reduce ores into iron to make steel. But that's not the only way we make steel, because as an industrialized nation, we have a lot of scrap left over from last year and years before. And so we take a lot of scrap and we combine it with a little bit of iron, typically direct reduced iron. Now, instead of reducing the ores via coal, we reduce the ores via syngas from natural gas. And that DRI, so-called direct because it's produced in a solid form, gets mixed with scrap into an electric arc furnace, an EAF, and that's the second way we make steel. And it's actually the majority way we make steel in the United States. And the last takeaway here is just that you take that steel and you turn it into steel products. And what I want you to take away from this slide is, while there are several places in the value chain that emit CO2, many of those are electrically driven, namely those EAFs and the fabrication piece. And so those are going to get cleaner as the electric grid greens. However, iron making is coal-based and is not going to get cleaner as the grid greens, and so that is what we focus on today. So how can we replace blast furnace iron making with new technologies? Well, let's look at the playing field for what technologies we might be able to use. So here on this trade space diagram, you see energy on the y-axis and emissions on the x-axis. There's our thermo-min, the 8.6 that I asked you to remember. So that's the floor for any iron-making technology. And what you see in the upper right-hand portion of the screen is, of course, that blast furnaces emit a lot of CO2, almost 2 tons per ton iron. And of course, they have a high energy use here. I've picked 19 as an example. Now, one of the most incremental things you could do is just slap CCS on top of blast furnaces. That will reduce your energy, that will reduce your emissions, not by 100% though, unfortunately, but it'll reduce it some, but it'll increase your energy use. Now, one of the main alternatives, like I said, is to take syngas from natural gas and reduce iron ores that way. There are less emissions with this process, and even less if you slap CCS on top of this so-called DRI process, but it's a little bit more expensive than using blast furnaces today. So even though it's in a better spot on our trade space diagram, folks don't use it as much. And also emissions aren't zero. So what we'll focus on for essentially the rest of the talk is technologies that can get to zero emissions and hopefully do so at cost. So I've unveiled some of these technologies. This is what we'll be talking about. And in particular, I want to say that it really depends on getting the cost down in order for them to be competitive at cost parity with the polluting technologies. And so from that perspective, let's look at the cost diagram. So shown here are the commercial routes, the blast furnace and the DRI, next to pilot CCS routes. And what you can see is that CCS is always more expensive, although it does decrease the CO2 emissions as shown in that red dot, but not to zero, unfortunately. Now, if you're going to move beyond carbon-based reductants, a main one that industry is interested in is using hydrogen. Now, hydrogen, unfortunately, is projected to be more expensive as a way to produce iron, but it would be potentially zero emissions. So at ARPA-E, we've been thinking about what are technologies that could be cheaper than hydrogen and zero emissions like hydrogen, perhaps on cost parity with CCS, but zero emissions. And so these technologies we'll talk about today, based on our cost modeling, have the potential to supplant blast furnace iron making at cost parity with adding CCS, but at zero emissions, shown in that red dot below. Finally, I just want to say, if none of these technologies work, there's still the backstop, which would be to do direct air capture of CO2 from the air and still continue to use blast furnaces. So this option sets a ceiling for the cost of new iron making technologies to need to beat. The first technology we'll talk about is in some sense the most incremental because it's a drop-in solution based on carbon, and that would be to use biomass. The energy use is high as shown here because you're essentially dropping it into the same way that we use blast furnaces today. Essentially, you take biomass and via production, turn it into bio-coke. Like I said, a benefit is it's drop-in, so it's mature. There's maybe lower retrofit, although you could consider new reactor techniques that are lower energy, but they wouldn't be retrofit. But the key challenge that we're seeing with this technology type is really what are the life cycle emissions of this technology? Biomass, of course, what land is that coming from, and what are the land use change emissions associated with that production process, including transportation. So R&D here really needs to focus on understanding what feedstocks and pathways would be viable from a life cycle perspective. Moving on to a second carbon-based reductant that you might consider. So this again is somewhat near term. Could you use sustainable syngas? So I mentioned that syngas, and in particular carbon monoxide, are the main reactants actually used in traditional iron making today. But in order to make it zero emissions, could you capture that CO2 and reform the flue stream in order to go back to syngas? This has the opportunity to have lower energy use than traditional blast furnaces. Like I said, it's mature reactant chemistry, but the devil is in the details, of course. You have to perhaps separate the flue stream gas into its various components, and of course reform this CO2, perhaps using clean electricity, all of which adds capital expenditure and cost. Now, you might envision a second category of sustainable syngas. What if you just, instead of looking at the red pathway, let's look at this orange pathway where the CO2 gets emitted to the atmosphere, but I'm calling this an open loop because CO2 is drawn down from the atmosphere to make syngas in the first place. So really the R&D has shifted to this front end where you'd have to do CO2 capture via, for example, direct air capture, or even having green plants do your CO2 capture for you, and this becomes a biomass syngas version. There are challenges, of course, associated with these technologies, and we're looking at options to de-risk these technologies in order to take advantage of this mature syngas chemistry. However, you might consider trying not to use carbon at all as a reductant. And one major route, as we've been discussing, is hydrogen. There's a problem with using hydrogen gas, though, and that is the carbon-based reactants are favorable because they are exothermic. They provide heat as they react. But hydrogen, its reaction with ores is endothermic. So reheating the reactor becomes more tricky. Folks that use gases are typically using carbon-based gases, and they're relying on that heat to be provided from within. Retrofitting a shaft reactor with some sort of heating possibility adds cost, of course. Hydrogen plasma is an interesting way to use a carbonless gas that gets around the endothermicity problem. You make hydrogen in whatever method you would have made it if you were just going to use the hydrogen directly, but then you turn it into a plasma, and that means essentially ionizing the hydrogen gas, so it's a more energetic, a more excited, a more ion and atom-based gas, essentially, and running that through the reactor, and that reacts with ores in essentially an exothermic way that's faster than if you just use hydrogen. And it's more retrofittable for gas-based reactors, the types of reactors that we already know how to build. However, this is somewhat of an exploratory technology, and getting the kinetics quite right is an interesting area of R&D. Now, the energy use for the hydrogen plasma-based iron making is basically exactly the energy use for just a hydrogen-based iron making route, namely the energy to make the hydrogen and then the energy to run the electric arc furnace. And both of these tend to be electrically based. So in particular, green electricity to electrolyze water and produce hydrogen is a main way that folks are considering to make hydrogen. Now, if you're going to buy green electricity and use that to make hydrogen to do iron making, what if you just skip the hydrogen step, instead taking electricity and directly reducing those ores? And that's what we'll explore in this next and final set of technologies, electrolytic iron making. Essentially, you take ores and you apply a voltage across them, splitting the iron and oxygen. An advantage of this technology is you don't have to go through hydrogen or any intermediate fuel, so it has the opportunity to be more efficient. But a main challenge is that production volume can be low because the rate can be low because electrolyzers are two-dimensional and gas-based reactors are three-dimensional. And this change essentially means that your mass and rate transfer limitations are more difficult for a two-dimensional reactor. And so R&D is focused on how do you turn 2D electrodes into 3D reactors, essentially. How can you make that current density as high as possible? I want to highlight two types of electrolytic iron making to show some specific R&D needs. First, high temperature electrolytic iron making. And this one uses a higher amount of energy because that electricity is heating the electrolyzer and heating the electrolyte. So this iron is coming out molten. And that has challenges because to contain molten iron, you need more expensive equipment, but the reaction kinetics are fast. So we're interested in R&D to provide this type of solution. It makes molten metal, which can go directly into an electric arc furnace. However, you might also consider low temperature electrolytic iron making from ores. And here we have the opportunity to use a lower amount of electricity, mostly because we've used a lower amount of electricity here. It's basically the same in the electric arc furnace. And there are benefits to this. Running at low temperature means you don't have to keep the reaction hot all the time, which means you don't have to be running all the time, which means you could use peak electricity when it's cheap to shave off some peak electricity from the grid. So you might be able to get cheaper electricity because you are time flexible with a low temperature iron making process. And of course, running at low temperature means you don't need high temperature stable materials that might be more expensive. But of course, there are challenges with this route, which folks are doing R&D to try to overcome. All in all, what we see with these several technologies is each of them has different risk profiles. And we see that this might imply that you could consider a portfolio approach for the iron making technologies of the future, whether your country or region has more or less sustainable biomass, more or less clean renewable electricity, or the ability to make hydrogen, for example. Or even CO2 storage capability that will be available in some areas that have reservoirs and not others. So the fact that none of these plots is very small, but each of them has different, a similar area, but different locations on this graph shows that iron making of the future really might be regional depending on the resources in that region. To summarize, in the last couple of minutes, we do see that even though these technologies are all different, there are some cross-cutting R&D needs that are common to all of them. First, new reactor designs are needed. You're not using coal anymore, and so we need to match to the types of resources that are available today, be it electricity, hydrogen, etc. Second, that modular reactors are needed for de-risking this technology, easing the path towards scale up. And finally, iron needs to be turned into steel in order to make steel products, and integrating with those steel makers is really crucial in order to promote changes as quickly as possible. We are finding, and in summary, we have found that low emissions technologies are not yet cost competitive, but there are several emerging ideas that have the ability to be cost competitive if scaled. And so we're interested in targeting R&D investment in order to achieve these goals. Finally, I'd be remiss if I didn't invite you to join our team. If you're interested in energy and emissions and funding researchers in the United States to do great work, please reach out. Happy to tell you more about our team. And here's my email address. Let me know if you want these slides. And thanks so much. Looking forward to the Q&A.
All right. Yeah, thanks, Christina. Great talk, really interesting. Definitely an important problem with a lot of options. So we're now moving into the Q&A portion of the session, and give maybe Christina a little bit of a break. I'm going to start with Dr. Krishnamurti, and we've also got Rick Ranhatra, who is also, I believe, from EPRI, who is also fielding questions. All right, so going back to some of the questions that came in from the first presentation, starting out, how do you quantify difficult to estimate non-energy benefits such as things like health and safety or environmental?
Yeah. Thank you so much for the question. So yeah, for the health and safety, that's a good, that's an interesting way of interesting non-energy benefit to quantify. One example that I can provide is like, say, for the boilers, like electric boilers, when they are chosen over oil-fired boilers. Then in that case, there are like very little, like there's no need for like fuel storage tanks, or there's no need to worry about leaking, which actually helps with the health of the, the safety issue. And that translates into less employee work time that's lost. So it is possible to like quantify roughly at a facility level. It can be quantified by finding out how many FTEs were lost in a plant due to like a oil leakage issue or something like that, and then try to monetize that. That's one way. But if we are trying to do a more standardized approach, it could be trying to have a percentage lost due to accidents, and then calculating the total monetary value of that, which are available from other like public sources. So that's for the health and safety. And then for the other environmental ones, those are somewhat harder. The easier one is the carbon emissions. So the carbon emissions reduction due to electric can be, there are many studies that have been done which do save, which do calculate the savings due to reduction in carbon, and having a dollar value for each ton of carbon that's emitted less. Hopefully that answers the question.
And have you already started looking at, or are there attempts at standardizing these calculations and processes for evaluation of non-energy benefits?
That's a really good way of looking as well, and thanks for that question. So one way that can be done is to by including non-energy benefits in the standardized cost tests, like the societal cost tests or the utility cost tests. And I believe that a few years ago, there was a presentation in this ACEEE summer study that did look at how different states are trying to quantify, trying to include non-energy benefits quantitatively into those cost studies. That was more for energy efficiency measures. So similar thing can be done for electrification measures.
Okay, great, thank you. And actually, there was a question to both you and Jonathan. So I guess I'll start with Jonathan, and Dr. Krishnamurti, feel free to add anything on top of that. But is operator training on new electric equipment or processes, that electrified processes, a cost that also needs to be considered in this calculation? So for Jonathan, when you're working with those customers, is that a concern or a real need?
Sure. I think in most of the applications that I've seen to data that we deal with, we're just talking about a different source of electricity, right? So the customer is already most of the time powering their equipment with electricity, so the operational aspects wouldn't change. What's different is what's happening, ahead of the disconnect switch. So before they would have had a diesel generator, they would have needed to know the operational and safety hazards of that. In this case, it would be grid supplied electricity. So there's actually very minimal effort, if any, that the customer needs to or should be doing when the grid is supplying the electricity. It does come with, the risk of electrocution, high voltage and all that. But most of the time, these have to be in vaults anyways. Electrical vaults are safe areas. There's protocols, there's OSHA requirements in place for exposure and arc flash and situations like that. And again, these same risks are not absent when it's being provided by a diesel generator. So I don't think there's a big gap in terms of operator training in most of the situations I see. It's actually a reduced requirement for most customers.
Yeah, I agree with Jonathan too. There is more like the gap. If there's any gap that can, however, be quantified if at all there is a clear gap by again using the same thing of how much employee time is taken up due to training and then quantifying that. And I'll also have my colleague Rick Ranhotra chime in on this, but essentially Jonathan has answered it really well. Yeah.
Well, I'll just quickly add that the example Srinidhi provided on, say, the infrared processing of food, that is a new animal, but in the process of the customer deciding to go that route, he's going to have to see it with his own eyes that it works. So there is a bit of a new process that has to be evaluated, but to both of their points, typically electrical is easier to control, and therefore the costs tend to be lower in the long run.
Great. Yeah. Just another question to Jonathan. I guess I had a question around how much of a driver your state's decarbonization goals played into the motivation and the capability for building the case for electrification. I'm also wondering, did the state provide, based on their goals, did they provide resources or other ways to facilitate those goals that you all could leverage? And then as a follow-up, do you have any thoughts on how to increase the scale of Vermont's electrification program?
Okay, so kind of a lot to unpack there, but I'll try my best. And to be honest, our partner utility here would probably be the best person to answer that question. But the state's effort to decarbonize puts an emphasis on this work. It also adds, as we saw, via the application of like the Tier 3 requirement within the renewable energy standard, it imposes penalties as well, which now adds an additional financial reason to pursue electrification, really is what it is. Most of the utilities, though, even before this came out, were pursuing electrification as a strategy as well, just to, increase their customer base, and it helps to fund all those infrastructure improvements, as we were saying before. So it's been an active item for distribution utilities all along, I do believe. There has been, a bit of a political lens put on it lately, just to try to motivate and get the next step beyond with electrification. And so going to resources, there hasn't been, the resources side in this case was a penalty. It wasn't an incentive. It wasn't grant money that was applied or given out to each. It was, more or less, it was kind of an alternative, like do this or else. So it might be unique in that way, but what it did really allow and promote was the type of collaboration we're seeing now, because utilities had to figure out quickly how to get a higher conversion rate with a limited budget that they have. So it encouraged them to get creative with working with new partners like they are now. And so I think, the fact that we've been able to do this partner with utilities, so far, Vermont Electric Co-op has exceeded their annual goals every year, and they're banking those credits forward. So that's been, kind of fruitful in helping get this all rolling. And there was a third part to your question, I think, that I'm
Yeah, just any thoughts about how to expand that?
Sure. Yeah, that's so. I just focus very narrowly on their clean air program, but all the utilities in the state are generally running programs right now for electric vehicles, electric mowers, cold climate heat pumps. There is a lot of electrification initiatives already on the table that are those programs are being run exclusively by the distribution utilities at this point. So they're pursuing electrification on multiple avenues. The examples I speak about today are really just on electrifying industrial manufacturers and more specifically, probably line extensions.
Okay, great, thanks. And I know we only have about 4 minutes left, and I want to catch the questions for Christina as well. So, Christina, are nanotechnologies being considered as a way to increase reaction volume area, move from the 2D to 3D?
Yeah, absolutely, Dustin. That's a great question, and that's exactly right. Essentially, you need to one way you might consider making electrolytic processes faster and higher throughput is to texture your 2D electrodes, and at a limit, nanoscale texturing is an example. Another example, we're considering is could your electrode take up an entire 3D volume because it's just a set of nanoparticles that are kind of all in a slurry together. So flow electrolysis is this type of work, and it's been known for batteries, like flow batteries, right, which are a grid storage technology. Can we port that type of idea into iron making?
Yeah, interesting. Would the source of hydrogen in the hydrogen case be water? And if so, is that a concern that folks are looking at, like what the impacts are on water use for hydrogen instead of CO?
Yeah, Prakash, that's a really good question, and I'll have to get back to you on some specifics. But water as a source of the hydrogen is a main thing that folks are considering, namely green electricity to split water. I don't know exactly if too many folks are thinking about it as a closed loop, and sort of essentially this is just going to be another need for processed water in the world. It would be stoichiometric with iron, so you're talking, a gigaton or so of water. Less than that, but yeah, it's a lot, but doable. This would be a main way. Another way would be blue hydrogen, which is CCS of the carbon part of natural gas, and the hydrogen part of natural gas would be used. That's another method.
Okay, great. And then I think we have time for just one last one. If you have any comments about where you see the most movement potential in the technologies that you mentioned. You mentioned a lot of different technologies. Just curious if there are any more promising.
Yeah. Global existing steel makers are most interested in making use of their existing capital, and then which uses carbon fuels like coal, and just taking the flue streams off and doing CCS. So that's where some of the main movement is. The existing steel makers are also pretty interested in hydrogen, especially in Europe. They're really interested in hydrogen. Natural gas is really expensive over there, so that's a reason. So we do see hydrogen as being a second area of large interest. In the United States, we're a little bit more sluggish moving forward, but we have seen interest in several of the technologies I've mentioned, low and high temperature electrolysis, etc. But essentially, the big steel makers want to fund stuff that uses their existing capital, and we're trying to encourage everybody to consider more exciting options as well.
Yeah, great, thanks. And I just want to thank our speakers one last time. So thank you all, great job, really interesting talks. I know we didn't get to all of the questions, but those questions that weren't addressed will get captured. There's also an opportunity for to ask questions and get them answered in the debrief session that we'll be having this afternoon around 5:15 Eastern time, where we will not only hear from our speakers, responding to your questions, There's also going to be a discussion on diversity, equity, inclusion, which is a really important aspect to manufacturing as well. So thank you again for attending this session, and we hope to see you this afternoon.